that I can cover in the remaining time. So, my name is Roland Kuhn. I'm working at TypeSafe, which is quite awesome because I'm paid to do open source work. That's fabulous. I really love it. I'm leading the Akka project at TypeSafe, but today I'm not talking about Akka. I'm also doing something else. Namely, I'm writing a book called Reactive Design Patterns. This is currently available in the Manning Early Access program and hopefully soon finished. It has been going on for quite a while, but that's what happens if you write a book next to a day job. I'm in chapter 14 of a planned number of 16, so it shouldn't be too far off. You can use this code 39KUHN to get 39% off if you want. I will talk in this presentation. I picked a few things that are in the book, but just a very small selection to give you an introduction of what this is all about. So, reactive design patterns, this reactive prefix, isn't that just a marketing gimmick? That's what, people usually say or ask or assume. Well, sure, I guess some people use it that way, but for me, it's actually something quite serious. I'm a co-author of the Reactive Manifesto, and the point of that is not to do some marketing buzzwordy thing, but to establish a terminology to set the stage in which we can discuss the problems that we are facing today and that we will face for the foreseeable future. So, a short introduction into what reactive is all about. Imagine you write a service, you come up with a brilliant new app, and you try it out, and then people start using it, and at some point, you reach the capacity that one machine can give you. You deployed it somewhere, it's on one machine that is handling all the requests, but this has a limit. It has finite memory, it has finite CPU. At some point, you cannot serve more users on this one box. What do you need to do? Well, of course, you buy compute power, you buy all the resources from the cloud, which means that you will now not have one machine that the systems are running on, you will have multiple machines. Sounds good in theory, only it completely changes the game in some respects. You cannot write the same program, the program in the same way and expect to be able to use like all of EC2 magically. That's not how it works. I guess most of the people here in this room know that. So we need to think about how we structure our program. Because if an incoming request arriving at a host which handles it triggers some actions at that host, and in order to answer the request, we need to coordinate between all the nodes that we deployed to. Let's say we scaled up to 1,000 nodes, and we need to ask all of them for a consensus on something. Then this coordination overhead will completely kill performance, will completely negate all the performance gains that we hoped to achieve by parallelizing onto multiple machines. This means that we need to partition our problem such that we do not need to share state, we do not need to coordinate between these hosts. So we have a distributed program that we will need to write in a different style than we wrote it before. What we gain by that is elasticity. If we do that, we can dynamically add and remove resources to our application deployment. If we just double the number of nodes that we have in the cluster, then we should see something like double the performance if we did it right. And if we don't need the performance, like you might know Netflix has an enormous fleet of servers that they need to run the video streaming, but there is a difference between different times of day in the bandwidth that they serve. The difference is a factor of 6. So it's like a curve like that, and if they kept the maximum deployed at all times, they would waste roughly half the money. So scaling down is as important as scaling up if you want to also have the cost effectiveness that is promised by the cloud. So that's what elasticity is about, and this is the first pillar of what reactive is all about. The second one is resilience. Resilience talks about if you have something and you deform it, or does it have the ability to get back into shape? Can it be repaired, or is it completely broken afterwards? We, of course, do not want our applications to fail in the face of failure. There are various things that can go wrong. We can have normal programming errors that stop our program, but we can have machine failures, we can have network outages, we can have power outages, any sort of failure that can bring down any machine in our network. Now, if you want to have an application that stays running, that keeps running when failures occur, you can defend against certain kinds of failures by managing them on the machine, by trying to catch them and repair them, but there are always cases that you cannot catch. For example, someone unplugs it from the power. Nothing you can do. The only thing you can do in order to survive such a failure is, well, to go beyond a single machine. It's the same thing again. We need to distribute the problem. We need to distribute the program. We shall not put all eggs in one basket, and that again means that we are distributing. We're doing distributed computing. Again, we need to write our program in a different fashion than we did before in order to fully benefit from it. In this time, it's not that we need to implement share nothing for performance reasons. This time, we do not want to share things because we want to minimize coupling between components so that failures don't cascade. If one component goes down due to a failure, it should not affect or infect all the others so that they go down as well. So that's the second pillar of what reactive is all about. So these are the two main characteristics that we want our programs to have. We want them to be able to scale up and down, and we want them to be resilient to failure. Result of this is responsiveness. That's the trait that Reactive Manifesto puts on top of the image that is in there. Elasticity leads to responsiveness in the face of varying load. So by being able to scale up and down the capacity of the system, we can adapt to the load and stay responsive, serve user requests even when there are 10 times as many users, for example. And resilience makes it so that we can stay responsive under failures. The system responds. So user makes a request, and there will be a response back from the system because it's resilient. This response might not always be the successful one because a crucial component might really be degraded. Or, I mean, a transatlantic cable is down. You just can't talk to the US right now from Europe. Yes, that can be. But it's then still better to respond with a failure because you have properly decoupled the components. So this one can still respond with a failure even if it cannot contact that one anymore. So that's responsiveness. We give users of the system feedback on that things are happening, and that makes them a lot happier. There were studies this morning, someone showed studies that this improved. So responding faster and giving people better feedback responds in more sales, more, I'm lack for words. Anyway, so the second one, well, I said we need to decouple things. For elasticity, we need to share nothing if possible, so as little as possible in order to minimize coordination and contention and so on. And for resilience, we need to decouple components such that bad behavior failures do not leak from one to the other. But what this also achieves is that we have clear boundaries between these components now that also contain implementation details much better than before. We can segregate the system along the dividing lines given by what responsibilities I have in my system. I have a component that has the responsibility to store files, and it does only that. And then I have a component that has the responsibility to interact with users and modify these files maybe. And they are completely separated from each other, which gives us all the runtime benefits, resilience, and so on. But it also enables us to split up this task such that two teams can work on it without stepping on their toes. They are also decoupled during development. This, by the way, I think is the core of what microservices should be about. It's the single responsibility principle that we are using here, which leads us to another result, which is maintainability. By decoupling, we have enabled all these components to be developed at their own pace so that we can have teams working independently of each other without, so we not only reduce the runtime coordination, we also reduce the development time coordination between the teams. This is all mirrored. Then, last, on the Reactive Manifesto, there is a fourth trait, and that is message-driven. I presented last year because the others, so we have elasticity and resilience as the desirable properties of our implementation. We have the high-level benefits, but all of this needs a foundation on which it is built. And, well, as we've seen, these systems are distributed. Distributed systems are characterized by the need for communication. You have components that are not local to each other, so you will need to send messages from A to B. And this is in your face. I mean, you see it everywhere. Messages can be lost. Messages take time to travel from A to B. These are characteristics that are different from making a local method call. So communication between components, asynchronous communication, is at the core of these systems. And this is why thinking about these is vitally important if you design such a system. You need to really concentrate on the communication protocols, on the conversations that happen in your system. You need to optimize the communication paths just like you do it in a human organization. It's really the same problem. If you have too much coordination overhead, too many meetings and so on, your projects don't make progress. So it's the same thing here. Software components also talk and shouldn't be too chatty and so on. It doesn't really matter how you do this communication. I mean, there are many different ways to do this. People say, well, you can use RPC. Well, I don't personally really like RPC. REST is something close to RPC. It's also request response, but the focus is more on transmitting a request and then asynchronous getting something back. I like that a bit better, but well, you can have message queues, message brokers that send things along, or you can use actors, of course. I mean, I'm Akka tech lead, so I'm a bit biased here. I admit that. But it doesn't really matter. The important point is that you need to be aware of how messages and how information is flowing in your system, and you need to model that explicitly. So this is the summary of how I'd like to view. This is what reactive is about. The values at the top row that I mentioned are not the only ones. You can find more. I think these are the most important ones, at least that I could identify so far. And we have these two pillars, elastic and resilient, and we need to think about the messaging that happens in our system. So far for an introduction. Now, in the rest, I will show you some patterns that are useful when implementing such systems that can be really helpful. First, we look at an architecture pattern. So this does not contain code. This is really about how you structure the application. And as I already mentioned, microservices, the single responsibility principle, I call it the simple component pattern. A component shall do only one thing, but do it in full. This means it has a responsibility, it does it, and it does all of that responsibility. This is, of course, not new at all. The earliest I could find was this book by DeMarco from 1979. where he said the goal is to maximize cohesion and minimize coupling to find your components. So you need to find those pieces of responsibility that really stick together, that cannot easily be disentangled. So you have one piece over here and you have one piece over there, but between them you have clear boundaries. This responsibility is only on that side, and the other responsibility is on this side. So if you have a text editor with a spell checker, for example, the text editing is a responsibility, the spell checking is a responsibility, but they really don't have anything to do with each other, really. You might want to combine them in one program, in a text editor overall, but the editing capability can run while the spell checker is down. It's not really needed. And you can also run the spell checker on the finished document without being able to edit it anymore. So these are completely different responsibilities that you separate, and then you have a dividing line, and everything you do afterwards, you know exactly in which bucket it goes, because you sorted it by responsibilities. Let's look at an example of applying this pattern. The example will be a batch job service. Batch job service is something that I had quite some contact with, and I was still doing my physics PhD at a CERT experiment. So that was like big data before big data. We had like 5,000 computers, and there was a system on which you could submit your jobs. They would be run. It was called OpenPBS, I think. I don't know who knows it here. And there were several interesting aspects. So you submit jobs, could be thousands of them, and then there's a second step, because it's quite contentious. I mean, you have these 200 physicists, and everyone wants to do their analysis to get their data out to write their publications and so on, and they depend on these jobs running. So there needs to be some fairness between what individual users do. There needs to be quotas, validation rules, like you cannot really request to run on one job on 100 CPUs. You're only allowed to use like a maximum 8 at a time and stuff like that. And then once you have validated and applied the constraints, the result of a planning run should be, well, you execute the jobs that were submitted that are currently in the queue in this order. The top of the queue is ordered such that these 5,000 worker nodes over there have a queue to pull work from. Then that's the third step. So we execute these jobs on some elastic compute cluster. Nowadays, I mean, back then we built that ourselves. Nowadays you just buy it, use EC2 or whatever. Then the fourth point, users can later come back and see how their jobs are doing. So this is the example use case. And we see, well, there's one responsibility that like we can cut off immediately where we recognize this is clearly separate from the rest, and that's running the things on the computing cluster. So I draw a picture like this. We say this execution, this concern here, that gets an ordered list of things to do, and it does them. That's a job, that is a specification that is sufficiently precise for a team to start working on. Now, on the left-hand side, we have the clients making requests, submitting jobs, and so on. And so between this and the execution, there is some sort of coordination that needs to go on, which needs to do complex things. And if you tell someone, write some coordination, that doesn't work. That's not specific enough. Nobody can really work from this description. So we know that this coordination box here, that is not yet a simple component. We need to split that up. So which parts shall it have? The users that connect from the left-hand side, that will be network connections. So there should be some like network server that listens on some port and which is accessible and that can take these requests. That's good. So we need some sort of client interface. Now, when you submit a job to this system, what you expect to happen when you get back the reply, yes, I have it, it's in queued. You expect it to be executed at some point. This means it needs to be ensured that it happens, even if someone just switches off the power right that moment. And this means that there needs to be some sort of persistent storage. We need to put these batch job descriptions to some storage in order to recover from outages and so on. Now, this storage will also need to be used by the execution component. It will need to retrieve the jobs. So if we just use a shared database or a distributed file system or whatever you want, then this client interface on the left-hand side and the execution on the right-hand side, not even speaking of the rest of the coordination, they will need to access the same information. They will need to make modifications to the same data. They need to update the status of jobs and so on. This means that there will need to be coordination at runtime between them. There need to be some locks or transactions or whatever you have. But it also means that the teams in developing these aspects will need to know how this space is managed. There is a big possibility for these to step on each other's toes. So this is not good. We need to split this out. This is why the next step looks like this. We have this client interface, we have the execution component, and we have some storage, and we know this storage is responsible for handling the status and so on. And we have clear interfaces for enqueuing things, for asking for the status, and for the execution component to query the thing as well and put back the results. And then, well, so these three things, we could let some teams start working on that. There is a piece missing, which is in red here, and that's the job scheduling. So you notice, when you say, do some job scheduling, well, if you have a really good team that knows what that means, they can maybe start working, but it's still a bit fuzzy. So we apply this process recursively. This is quite important. We might want to separate out different parts. One part of this is the job scheduling needs to present this ordered list of next things to do to the execution. So this is a really important aspect of it. It also needs to validate incoming requests, whether they match selection criteria, rules, whatever, quotas. And it also needs to do planning runs. And, well, they are quite independent from each other. Doing a validation of some job is completely independent of planning the things. So these are separate responsibilities. So the image evolves like this. Now, you've seen that there were two steps of recursively breaking down things, and now we've reached something that, yeah, starts feeling a bit more concrete, and so on. We could start working on it. This is a process that you need to do recursively until you have reached simple components. But one word of warning, it's easy to get carried away. I mean, you can do that too far as well. If you split it down further and further, you will not end up with simple components. You will end up with trivial components that have no reason to exist. And then you just create more busy work. I guess there are people who like that. I don't think that's the goal. So you need to keep in mind that there is a limit to this. So this is the single component, simple component pattern, and the example for that. In the remaining, like 15 minutes, I show you some, well, I have not yet found a good word for this. They are not architecture patterns, they are really like code patterns that you use when you implement things. There are some that are really well known, and people have covered them in the past. For example, the circuit breaker pattern. I just name it here because it's so useful. And this is, and to show you what the kind of patterns are that we're looking at. Circuit breaker, it's kind of an analogy to electrical engineering that does not quite work. It's more like a shunt, I think. Protect services by breaking the connection during failure periods. So what you do is, if you make a request to another service and the response does not come back in time, consistently over some period, that's a good indication that the service is overloaded. Or if it comes back with failures, 5 times in a row, that's a good indication that there is something wrong that is just, it's not that kind of transient that it's going away right away. There might be some failure that just takes a few minutes to resolve. So instead of hammering that service with even more requests, which would be really detrimental in the overloaded case anyway, we just trip the circuit breaker. When the circuit breaker opens, we do not actually make the requests anymore to that component. And that frees the component to recover more quickly, and especially if it was an overload situation. And it also means that we get back the negative responses that we would have gotten back with a large timeout later anyway, most likely. We get them back immediately, so we can respond earlier. The system stays responsive under failures. This is the primary tool for decoupling one service from another service that it uses. So if this fails, this can still stay operating. It can stay up and still do useful things. Maybe not to its full functionality, but at least it can tell its client, I'm doing a degraded job here, or I'm temporarily not capable of performing my job. But it stays responsive. These circuit breakers are available in some libraries. So you don't code them yourself. Typically, Akka provides one, which is this circuit breaker thing here in the lower middle part. You just configure it with the parameters, how many failures trip it, and so on, and what the time constants are. So after which time it goes into half open again, and then how long it stays closed, and so on. And what the expected maximum service call time is. And then you just need an API that returns a future. This is crucial. You need to make it asynchronous, otherwise you cannot really use a circuit breaker, because making synchronous calls is not something that you can really interrupt, that you can really work with. There is no decoupling that you can achieve if you use synchronous calls. This is why I don't like RPC, because RPC usually focuses on providing synchronous APIs for things that are in fact asynchronous. So once we have this send to storage function that returns a future, we can just execute it with a circuit breaker here. And this circuit breaker will monitor the situation, and when things take too long or when things fail too often, the circuit breaker opens and we get a circuit breaker open exception instead of a real answer from the service. And then we will turn that back into a response that we are going to give to our clients. So, circuit breaker. So nice. I think Martin Fowler has comprehensive articles on that as well. So I'm not claiming that any of this is new. The next pattern is probably too simple to be interesting, you might think. I still find it interesting to realize how this pattern works. The request-response pattern is the simplest possible conversation that two parties can have. There is no conversation if there's just one message. So there's two messages, a conversation, request, response. That's the simplest possible. And in order to make that work, we need to include a return address in the message so that the response can be delivered to the right recipient. In a diagram form, these are the two participants, A and B. A sends a request to B, and this dashed line means it includes its own address. And that gives B the power, the possibility, the ability to send back the second message to A, because otherwise it wouldn't know where or who A is. Well, this is very logical. Everyone who has written a letter has done that. But it's easy to miss in most of the modern protocols that we use, because the request-response pattern is the single most frequently used one that we have today. It is the most primitive conversation, but it's also one that has some compositional properties. If you want to combine more complex protocols, you run into really difficult academic problems. But request-response is reasonably simple to understand, so it's usually modeled implicitly. For example, if you have an HTTP connection, the HTTP request, including its headers, does not include the return address. It's nowhere in there. because the return address is implicit in the underlying TCP connection. The TCP packets, each of them has the source, port, and IP address of the sender. And this is how the responses get relayed back. So HTTP is really cheating in this regard, well, for good reasons and so on. But it's easy to overlook that the return address is actually included. In Akka, we found in versions 1 and 2 that it is so useful to do this that we have this automatic sender capture. When trying to develop Akka typed, I ran into real problems and had to remove it. So in Akka typed, you have to be explicit about including the return address in the messages that you send. So that's, yeah, you could call that a technicality maybe, but if you look at message queues, like if you want to do this using AMQP, then there is no such thing as a return address that is automatically managed. If you want this component to send to that component, it will need to know the queue name on which that is listening. And if it wants to receive a reply, it will have to own a queue itself on which it is listening, and it will need to include the queue name in the first message, and then the second comes back over the other queue. In order then to correlate that this is actually the request that triggered that response, you also usually need a correlation ID, because usually these components that you have are long-lived. You could have this email sending service and the invoicing component, and they are not created per invoice. They stay up and running. So they need correlation IDs to figure out what has been answered and what not. There are ways around this. If you use actors, for example, you can just create a short-lived child actor that you use as the return address, and then in the identity of this actor, the correlation ID is basically encoded. That's how it travels back and forth. But that's just a shortcut. It does nothing else but model a correlation ID. So this is request response. But the last pattern that I'm talking about is probably the most interesting one. Unfortunately, or fortunately, I should say, it has been covered this morning already by Martin Kleppmann. I think better than I can cover it here. So the Saga pattern says, divide long-lived and distributed transactions into quick and local ones with compensating actions for recovery. This pattern, the formulation of this pattern and the inclusion in my book is a result of speaking with people. And when we talk about microservices or any sort of reactive systems, people really run into these questions. We have a microservice architecture where knowledge is distributed, but these participants, these microservices, are supposed to own their data exclusively. This means if I have a business level process or transaction that is going on that affects more than one microservice, we would have to have transactions that span multiple microservices. But for various reasons, it's really a bad idea to implement that in its classical form. Distributed transaction managers are not as reliable as they should be in order to be theoretically safe to reason with. And they're, worst of all, I mean, performance is not really their strong part, let's just say, because of all the coordination overhead. That's clear. If you need to reach consensus between these 10 microservices about something, that will completely kill performance. And as Martin mentioned this morning, it also spreads the possibility for error. If just one of them is down, then they will not reach consensus and things will fail. So we cannot have these transactions. So what do? Well, we have use cases that currently are modeled like that and that use them. So my hero in this regard is Pat Helland. The first paper, Life Beyond Distributed Transactions, goes into detail about why distributed transactions cannot really work and how you should do it instead. And the answer is you need to partition your data so that all the things that you do, all the operations that you perform remain local. So you partition it into pieces, and no transaction can span these pieces. Everything stays within one realm, and these realms are local things. And the second one, memories, guesses, and apologies, talks about how to basically implement atomicity in the absence of these distributed transactions. And the idea for this, I mean, this is all not new. The same reference was in the talk this morning. Sagas, formulated by Garcia Molina and Salem, already in 1987. I start with an example of explaining how this works. If you have bank accounts, X and Y, and you want to transfer money between them without locking both of them, how do you go about this? Well, you split it up into two transactions, T1 and T2. T1 will transfer the money from X into a local working account. This can preserve some local database invariance, like the money is not lost, right? It's just shifted from X to the working account. And then T2 transfers the money from the local working account to Y, again, preserving invariance and so on. Now, the new thing, because we have broken up the process, if something goes wrong after T1 commits and before T2 commits, we need to somehow roll back. And the database doesn't know how to do that because, well, T1 has committed, so there's nothing the database will do for us. So we need the compensating action, C1, which will just transfer the money back into the account of X in this case. What the authors of the paper note is that writing these compensating actions it has the same difficulty or complexity as writing the real transactions that you want to write. So this is not something that's really worrisome or black magic or so. Yeah, so of course there is one drawback or important property this has. If you have concurrently running sagas, they can now, so if they are only aware of accounts X and Y and do not know about the local working account, then for them it might look like money is missing while it's in flight. So other sagas can see intermediate states. And you need to be able to break your transactions up in this way that does not really invalidate your business case. So it is sometimes difficult to do that. Sometimes it's not even possible. And then, well, you cannot distribute. That's the simple conclusion. So in a bit more formal terms, we can do backward recovery. If we have 4 transactions, the first 3 committed, then we run the compensating actions in reverse order, C3, C2, C1. The other possibility described in the paper is forward recovery, but for that you need save points. So you do T1, and then as part of T1, most likely, or it would be appropriate if possible, you store that you have done T1. That's a save point. After doing T2, you have a save point that says, okay, I have done that, and so on. And when the machine crashes and comes back online, it sees that this saga is not yet finished, and it sees which part of the saga has been committed already, and it can then start from that point onward and complete the sequence. That's forward recovery. So, yeah, as I said, this needs to be persistent. The paper was written in 87. They didn't really have distributed databases or lost something. The main problem that the paper was dealing with was long-lived transactions and making the database more performant. Now we're doing it for fault tolerance, resilience, and so on reasons. So we will need to make the sagas persistent anyway. So in order to I should probably ask, are there questions for that? If not, I can show you some code, but I'm not sure whether the remaining 3 minutes are enough to show all of it. So I have implemented this process in Akka, using Akka persistence as an example. And here are just the message types and event types defined. And the general principle is that this saga is a persistent actor, and it will do things exactly as I wrote down. When it gets the transfer, it persists that it wants to do the transfer. That's the first save point, so to speak. Then when that has been done, it does withdraw money. So it does the first transaction. This is a method on the account that returns a future in this case. And it maps it to money withdrawn. When that is done, it persists that. That's the second save point. The important point here is the included ID field, because here the save point is not committed as part of the transaction. It's done outside. This means that we might crash between committing the transaction and doing the save point. And this means we need to make the transaction idempotent. And well, for this, I have foreseen this ID in this implementation so that the withdraw method can see, oh, I have done this already. I won't do it again. I will just say, yeah, it's done. Yeah, and so this just goes forward with all the steps until the process is finished. And then during recovery, you just need to figure out, so you see all the save points that you have done as events that come back from the log, and you figure out where to, well, restart your process, where you were. The interesting thing here is, when I read this paper, it felt really like this is like reactive going back full circle. Search for natural divisions of the work being performed. That's the single responsibility principle. It is the database itself that is naturally partitioned into relatively independent components. These are microservices that own their data exclusively. So I felt reminded of many of the things that we're talking about now in a paper from '87, which kind of makes it feel good. So I think I should come to the conclusion. Reactive systems, I hope I convinced you that, I mean, the values are not just marketing buzz. There is something that we really need to solve. And these problems that we're solving, well, force us to go distributed. And this requires some new architecture patterns and tools and so on. Most of them are not new. Most of them are really old. But, well, while none of this is really that easy and you need to keep thinking, for me, this is lots of fun because it's so close to how we operate as a society. It has all the same problems of coordination, conversations, and so on. So I think it's just fun to work with. Thank you.